There are moments in the pursuit of knowledge when the universe in its infinite and silent grandeur decides to break its own rules. Moments when a truth we hold to be as solid as bedrock simply evaporates, leaving us adrift in a sea of profound and unsettling questions. For generations, we have pointed our instruments toward the heavens, learning to read the starlight to decipher the ancient language of the cosmos. We learned that objects have a nature, a fundamental identity etched into their very substance and reflected in the light they cast back at us. A star of a certain type has a specific spectral signature. A planet rich in methane will have a particular hue. These were the foundational laws of cosmic observation, the grammar of our celestial dialogue. And then a wanderer arrived from the interstellar dark, an object designated 3I, Atlas, and it began a conversation that would shatter our certainty. It didn't just challenge our assumptions, it performed an act of cosmic alchemy right before our eyes, a transformation so impossible it felt like a violation of reality itself. This is the story of that impossibility of a mystery that began with a whisper of light and grew into a roar that echoes through every observatory on Earth. It is the story of a rock that changed its soul, and in doing so forced us to question everything we thought we knew about the universe and our place within it. It began as so many modern discoveries do not, with a lone astronomer peering through an eyepiece, but with the tireless, unblinking gaze of a machine. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, is a network of robotic telescopes standing guard over our planet. Its sole purpose is to scan the entire visible sky every few nights, a silent, sleepless sentinel searching for anything that moves against the fixed backdrop of the stars. It hunts for danger for rogue asteroids on a collision course with Earth. But in its vigilance, it sometimes finds ghosts. It catches faint ephemeral travelers passing through our cosmic neighborhood, visitors from realms we can only dream of. On one particular evening, the sophisticated software flagged a new point of light. It was impossibly faint, a mere handful of photons captured from the abyss, but it was moving, and it was moving fast. Crucially, its trajectory was not a gentle, familiar ellipse, the signature of an object gravitationally bound to our Sunday. This was a hyperbola, a searing, open-ended arc. This was the unmistakable calling card of an outsider, an object not born of our solar system, but one that had journeyed for millions, perhaps billions of years, through the cold, empty void between the stars. The astronomical community ignited. We had seen such visitors before, but they were fantastically rare. First, the enigmatic cigar-shaped Oumuamua, which tumbled past us too quickly for a proper look. Then the more conventional but still extraordinary comet 2I, Borisov. Each was a priceless scientific treasure, a physical sample from another star system delivered directly to our doorstep. 3I. Atlas was only the third confirmed interstellar object in human history. Every major telescope on and off the planet swiveled to stare at this new celestial refugee. The first order of business, as with any new discovery, was to determine its nature, to read its story from its light. This is done through a process called spectroscopy, a technique that acts like a cosmic prism. By splitting the faint light from Atlas into its constituent colors, its spectrum scientists can identify the chemical elements and compounds on its surface. It is a fingerprint of its identity. The initial data that streamed back from the world's great observatories was both thrilling and, in a way, comforting. The spectral fingerprint of 3I Atlas was overwhelmingly, unequivocally blue. Now, in the cosmos, color is not an aesthetic choice. It is a profound statement of history and composition. A blue hue on a distant icy body tells a very specific story. It speaks of a surface dominated by exotic ices that only form in the most frigid, remote corners of a planetary system. We see this otherworldly blue on Neptune's moon Triton, a captured world from the Kuiper Belt whose surface is a crystalline landscape of frozen nitrogen. We see it on Pluto, where mountains of water ice float upon vast, churning glaciers of solid nitrogen and methane. This particular shade of blue suggested that 3I, Atlas, was born in a place of unimaginable cold, a place far beyond the frost line of its own native star, where nitrogen, a gas that makes up most of our own atmosphere, freezes. Solid. The implications were staggering. This tiny messenger was telling us that the building blocks of worlds, even worlds with nitrogen-rich surfaces like our own Earth, were not unique to our solar system. It hinted at a universal architecture, a common set of ingredients scattered across the galaxy. Papers were drafted, models were run, a consensus began to form. 3I. Atlas was a fragment of a distant Pluto-like world, a chip off an alien ice dwarf ejected from its home system by some long-forgotten gravitational cataclysm. It was a beautiful, elegant, and scientifically sound explanation, and it was completely, utterly wrong. The moment of revelation did not arrive with a thunderclap or a brilliant flash. It came quietly as a stream of anomalous data points, appearing on a computer screen in a darkened control room. At first it was dismissed as an error, a calibration issue with the telescope's sensitive instruments, perhaps a temporary distortion from Earth's own turbulent atmosphere. The team running the observations on that particular night would have checked their systems, rerun their diagnostics, and prepared to discard the corrupted data. But the anomaly didn't go away. Another telescope thousands of miles away reported the same thing. Then a third. A wave of frantic communication began to ripple through the global astronomy community, a cascade of emails and urgent phone calls crossing continents and time zones. The message was the same everywhere, and it was laced with a growing sense of disbelief and wonder. 3I Atlas was no longer blue. In the span of just a few days of observation, its entire spectral signature had undergone a radical, violent metamorphosis. Where there was once a clear, cold blue, there was now a deep, rich, and profoundly organic red. The change was not subtle. It was not a gradual tinting or a minor shift in wavelength. It was a complete and total chromatic betrayal, as if a sapphire had spontaneously transmuted into a ruby. Such a thing had never been witnessed before. Comets can brighten as they approach the sun, and their ices vaporize, forming a glowing coma. Asteroids can fragment, revealing fresh material underneath. But a fundamental system-wide change in the intrinsic surface color of a solid body happening on a timescale of mere hours. It was, by all accounts, physically impossible. It was as if the moon suddenly turned green, or Mars shed its rusty red for a brilliant violet. It violated the principle of inertia that governs not just motion, a body in motion staying in motion, but also nature, that a body of a certain composition stays that same composition unless acted upon by an overwhelming external force. And the sun, at this vast distance, was far too weak to be that force. The scientific community was thrown into a state of exhilarating chaos. The beautiful, simple story of a nitrogen ice fragment was shattered. The pre-written papers were scrapped. The elegant models were discarded. Scientists were faced with a cosmic crime scene. The victim was our understanding, and the evidence was this baffling color-shifting rock. The new red color was as telling as the original blue, but it told a completely different and far more complex story. In our own solar system, a reddish hue is the signature of tholins. These are not a single chemical, but a complex sticky sludge of organic macromolecules. They are formed when ultraviolet radiation from the sun, or high-energy particles trapped in a planet's magnetic field, irradiates simpler molecules like methane, ethane, and nitrogen. This cosmic radiation cooks these simple ices, breaking them apart and reassembling them into long, complex carbon-based chains. Tholins are what give the hazy atmosphere of Saturn's moon Titan its orange-brown color. They are the dark reddish patches that stain the surface of Pluto and many other objects in the Kuiper belt. They are in a very real sense the precursors to life. These molecules are a crucial step on the long chemical pathway from simple, inert matter to the complex biology that eventually led to us. And now this interstellar visitor was drenched in them, but this revelation only deepened the mystery to an almost unbearable degree. How could an object be both things at once? How could it present a pure nitrogen ice blue one day and a complex organic red the next? The questions came in a torrent, each more profound than the last. Was the blue surface merely a thin, fragile veneer, a layer of frost accumulated over its long journey through the interstellar medium, which then sublimated away as it neared our sun, revealing its true ancient reddish face underneath? If so, this would mean that the surfaces of these wandering bodies are not static but are actively painted and repainted by the near vacuum of deep space. It would suggest that interstellar space isn't empty but contains enough material to coat a traveler over millions of years. Or was the process more violent? Did 3I, Atlas, undergo some kind of internal eruption, a cryovolcanic event where slushy, nitrogen-rich organics from its interior burst forth, explosively blanketing its original blue surface with fresh, red material? This would imply that even this small, frozen rock was a geologically active world, possessing a hidden inner warmth and a dynamic core, a truly shocking concept for an object of its size and presumed age. Or, and this was the most tantalizing and disturbing possibility, did we witness the creation of the tholins in real time? Could it be that the blue nitrogen ice on the surface was not a covering but the raw fuel, perhaps a sudden intense burst of radiation? Maybe an unseen solar flare or a wave of powerful cosmic rays struck the object, flash cooking its surface and triggering the chemical reaction that transformed blue nitrogen into red organics right before our eyes. If this were true, it would mean the universe is a far more dynamic and creative place than we ever imagined, capable of forging the building blocks of life on the fly, on the cold, dark surfaces of wandering worlds. This single, unprecedented astronomical event has plunged us into a desperate and exhilarating quest for answers. The color of 3I, Atlas, is not just a curiosity, it has become a cosmic Rosetta Stone. What is the true nature of this alien rock? What cosmic process, either gentle or violent, could trigger such a profound transformation? And most importantly, what does this chameleon from another star tell us about the birthplaces of other worlds, the distribution of life's essential ingredients, across the vastness of the galaxy and the fundamental nature of matter itself as it endures the lonely pilgrimage from one sun to the next? This small, distant point of light is no longer just an object of study. It is a messenger carrying a secret from a star we will never know, and a challenge to the very core of our astronomical knowledge. And its story is only just beginning. Imagine a message adrift for 1 billion years, not written in words but in light and ice. A silent traveler cast out from its home star and sent tumbling through the unimaginable loneliness of the interstellar void. For millennia, humanity has looked up and seen only the distant, steady glow of other suns, each one an island in a black ocean. We wondered if we were truly alone, not just in life but in matter. Were the building blocks of our own solar system unique, or did the cosmos churn out planets and comets with a familiar universal recipe? For the longest time we had no way of knowing. The distances were simply too vast, the travelers too small and too dark. They were ghosts in our equations, statistical certainties that had never once graced our telescopes. A stray comet from Vega, an asteroid from Sirius, these were the stuff of scientific fantasy. Then in 2017, the fantasy became a reality. Our sky, once a closed and familiar home, was suddenly visited by a stranger. It didn't move like anything we had ever seen before. It wasn't bound to our sun by the gentle, predictable leash of gravity that holds our planets in their elegant waltz. Instead, it was on a trajectory of escape, a cosmic slingshot that would carry it in one side of our solar system and out the other, never to return. We called it Oumuamua the Hawaiian, for a messenger from afar arriving first. The name was poetic, but the object itself was a profound enigma. It was small, dark, and spinning strangely. Its trajectory showed a slight, inexplicable acceleration away from the sun, a nudge that wasn't caused by the venting of gas and dust we see in our own comets. We were captivated and utterly baffled. Speculation ran wild from a fragment of a Pluto-like world made of nitrogen ice to something far more engineered. Oumuamua gave us no time for answers. It was a fleeting whisper, a brief and mysterious silhouette against the light of our star, and then it was gone, vanishing back into the endless night from which it came. It left us with more questions than we started with, and a tantalizing, unnerving sense that we had just witnessed something truly extraordinary. It had opened a door proving that the gulf between stars was not empty, but was in fact a highway for cosmic nomads. Just 2 years later, a second visitor arrived. This one, named 2I, Borisov after its amateur discoverer, was a welcome relief. As it neared the sun, it sprouted a magnificent coma, and tail a familiar shroud of gas and dust. It looked for all intents and purposes like a comet. A comet from here. Its composition was reassuringly familiar, rich in the same kinds of molecules we find in the comets born in our own celestial backyard. Borisov was our cosmic anchor. It proved that Oumuamua wasn't a singular hallucination, and that at least some interstellar travelers were made of the same stuff as our own. It grounded our theories. It suggested that planetary systems, at least some of them, form in similar ways across the galaxy. With a sample size of 2, we had established the boundaries of our new reality. One visitor was an unsolvable riddle, a strange rocky shard unlike anything we knew. The other was a comforting confirmation, a cosmic cousin that made the galaxy feel a little less strange. We now knew the visitors were out there, and we were watching. We were waiting for the third. We were ready to place it on this nascent spectrum of cosmic possibility. Would it be weird, or would it be normal? Would it deepen the mystery, or would it build our confidence? The watchtowers of this new frontier are not silver domes on lonely mountaintops, but arrays of robotic telescopes. They're digital eyes capturing the entire visible sky every few nights. They are relentless automated sentinels, chief among them the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Based in Hawaii, its mission is not to ponder the mysteries of the cosmos, but to perform a far more urgent task, to find any rogue asteroid on a collision course with Earth. It is a planetary defense system scanning for faint smudges of light moving against the backdrop of fixed stars. Night after night, its telescopes photograph vast swathes of the heavens, and sophisticated algorithms analyze the petabytes of data, searching for the telltale streaks of nearby objects. It is a hunt for bullets, not for ghosts, but in searching for threats from within our system, Atlas had also become one of our planet's foremost detectors of messengers from without. Inside the data stream, where algorithms flag thousands of potential moving objects every night, human intuition remains the final, crucial filter. For Dr. Irina Rostova, a planetary scientist working with the Atlas survey, the routine had a familiar rhythm. Her screen would fill with candidates, known asteroids on their predictable paths, fragments of satellite debris, even cosmic ray hits that tricked the software. Her job was to sift through this digital noise to find the single meaningful signal. One evening, an object flagged by the system caught her eye. It was exceptionally faint, a barely perceptible cluster of pixels. But it wasn't the faintness that was unusual. It was the path it was carving through space. The software had calculated a preliminary trajectory, and the number it returned made her pause. The eccentricity was greater than 1. For an astronomer, that number is a thunderclap. It means the object is not in a closed elliptical orbit bound forever to our Sunday. It means the object is on a hyperbolic path, an open-ended journey. It possesses too much energy, too much velocity to be captured. It was a clear and unambiguous sign. This was not one of ours. This was another traveller from the interstellar deep. The alert went out across the globe. This is the modern miracle of astronomy. A discovery made by one telescope is not a private secret, but a call to arms for the entire scientific community. Within hours, the world's greatest observatories began to pivot their colossal mirrors toward the precise coordinates. In the high, thin air of Chile's Atacama Desert, the European Southern Observatory's very large telescope turned its attention away from distant galaxies. On the sacred peak of Mauna Kea in Hawaii, the twin Keck telescopes, each with a primary mirror 10 meters across, prepared to stare into the visitor's soul. Even the Hubble and Webb Space Telescopes, orbiting high above the distorting haze of Earth's atmosphere, were tasked with intercepting this fleeting guest. A global network of human ingenuity, a planetary immune system of sorts, was mobilizing to characterize this ghost before it could slip through our fingers. The race was on. Every photon of light collected was a priceless clue. The first question you ask of any visitor is, where do you come from? But for an object from another star, that is the ultimate and perhaps unanswerable question. The more immediate and revealing question is, what are you made of? And the first most powerful tool for answering that is to simply look at its color. In astronomy, color is not an aesthetic quality. It is a profound diagnostic tool. By measuring the precise amount of light an object reflects at different wavelengths, from blue to green to red, scientists can decipher the chemistry of its surface. It's a form of long-distance geology, a cosmic fingerprinting. The technique is called photometry, and it is the first portrait we paint of any new object in the sky. As the initial data from the global network of telescopes poured in, a consistent picture began to emerge for the object now officially designated 3I, Atlas. It was neutral, almost grey, with a slight preference for reflecting blue light. To a layperson, this might sound unremarkable, but in the specific, nuanced language of small-body astronomy, this was a monumental discovery. Most of the asteroids and comets within our own solar system, particularly those that have spent billions of years orbiting in the outer reaches, tend to be reddish. This ruddy hue is the result of what's called space weathering. Over eons, their surfaces are bombarded by a relentless shower of high-energy cosmic rays and scorched by the solar wind. This constant irradiation breaks down simple molecules on the surface, like methane ice and carbon monoxide, and reforges them into complex carbon-rich organic compounds called tholins. These tholins are dark, sticky, and deeply red. They are the cosmic equivalent of a sunburn, a patina of age baked onto the surface. Think of a piece of pristine rock left out in the harsh desert sun for 1,000 years. It weathers it, darkens it, reddens. Most of the objects in our Kuiper belt, the donut-shaped ring of icy bodies beyond Neptune, display this characteristic reddish tint. They are ancient and weathered veterans of our solar system's history, but 3I, Atlas, was not red. Its bluish-neutral color told a completely different story. It suggested that its surface was fresh, unprocessed, and pristine. It was as if we had reached into the cosmos and pulled out a freshly quarried stone, one that had been shielded from the damaging effects of space radiation for its entire existence. This color signature was consistent with a surface dominated by water ice, or perhaps fresh silicate rock that had never been significantly processed by a nearby star. It was a surface that looked new. This was our most important clue yet. A blue color implies that the object must have originated from a place where it was protected from the harsh environment of space. It pointed to an origin deep within the frozen heart of a vast cometary reservoir, a place analogous to our own Oort cloud. To understand the significance of this, you must journey back in time to the chaotic birth of a star system. Imagine a young star, newly ignited, surrounded by a vast spinning disk of gas and dust. Within this protoplanetary disk, gravity begins to work its magic. Dust grains stick together, growing into pebbles, then boulders, then planetesimals, the building blocks of planets. It is a violent, turbulent era of cosmic construction. Giant planets, like our Jupiter and Saturn, begin to form, and their immense gravity turns the disk into a chaotic shooting gallery. These gravitational behemoths act as cosmic bouncers, flinging smaller planetesimals in all directions. Billions are consumed by the parent star, and billions more collide and merge to form the rocky and icy planets we know. A significant fraction are herded into stable regions, forming asteroid belts close to the star and vast reservoirs of icy bodies, like the Kuiper belt in the frozen suburbs. But some of these planetesimals, through a chance gravitational encounter with a giant planet, are given a final violent kick. They are accelerated beyond their star's escape velocity. They are ejected. Cast out from their home system, they become the galactic wanderers, the interstellar objects we are only now beginning to detect. The theories predicted that many of these ejected bodies would come from the outer, colder regions of their native planetary systems, places where ice could readily condense. Once flung into the interstellar medium, they would spend millions or even billions of years in a state of near-perfect hibernation. The deep freeze of the void, just a few degrees above absolute zero, would preserve their primordial composition. The darkness between the stars would shield them from the intense radiation that weathers the objects within a system. They would be in effect perfect time capsules carrying an unspoiled chemical record of the raw materials and conditions that existed when and where they were formed. The pristine blue color of 3I Atlas was a stunning confirmation of this elegant and powerful theory. It fit the narrative perfectly. Here was a visitor that wasn't a bizarre, unexplainable enigma like Oumuamua. Nor was it just a simple comet like Borisov. It was something more profound. It was a pristine building block of another world delivered directly to our doorstep. It was telling us that it came from the cold, dark, protected nursery of its star system, a place where its surface was never corrupted. Its blueness was a certificate of authenticity, a testament to its long, cold journey through the abyss. Scientists around the world breathed a collective sigh of relief and excitement. The models were working. Our understanding of how planetary systems form and evolve, a picture pieced together from studying just one system, our own, seemed to hold true across the stars. We had found our perfect interstellar specimen, a pristine relic from another sun behaving exactly as it should, its color a beautiful and simple confirmation of our most cherished theories. For a few precious weeks, the story of 3I, Atlas, was coherent, elegant, and wonderfully complete. The global observation campaign continued, tracking its every move as it drew closer to the sun, its trajectory bringing it nearer to Earth for its one and only flyby. Every telescope that could be trained upon it was gathering more and more detailed information about its composition, its rotation, its essence. The scientific community was buzzing, preparing to write the definitive chapter on the nature of these interstellar messengers. The story was, for all intents and purposes, already written, but the universe rarely tells simple stories, and it pays little heed to human expectation. As 3I, Atlas, continued its inexorable fall toward the heart of our solar system, its light, that pristine blue light which told us so much, began to carry a new message. Faintly at first, and then with undeniable clarity, something began to change. A message that would not just add a new chapter to the story, but would force us to tear the whole book apart. And so, for a time, a fragile consensus held. The initial spectrograms of 3I, Atlas, painted a portrait that was both alien and in a strange way reassuringly simple. Its light, filtered through the immense prisms of our best telescopes, was unequivocally blue, a cool sapphire glow against the velvet black. This single fact became the bedrock of every nascent theory, the primary clue in a cosmic detective story spanning light years. Planetary scientists accustomed to the muddy browns and ruddy ochres of our own system's asteroids and comets saw in this blueness a pristine surface, perhaps coated in exotic ices like solid nitrogen or carbon monoxide, flash-frozen relics from the frigid molecular cloud where it was born. It was a messenger from a place unimaginably different, yet it seemed to obey laws of physics we could comprehend. For weeks that stretched into months, this was the story we told ourselves. As 3I, Atlas carved its silent arc across the orbits of Mars and Jupiter, observatories around the globe, and in orbit above us, kept a vigilant, almost paternal watch. Each night its position was logged, its brightness measured, its spectral signature captured and archived. A global network of astronomers linked by encrypted data streams and late-night video calls meticulously built a four-dimensional map of this transient visitor, its path, its speed, its rotation, and its chemical fingerprint. The work was routine, yet tinged with a constant simmering excitement. We were charting the unknown, but the chart itself seemed stable. The narrative felt secure, then the first discordant note appeared. It wasn't a sudden, jarring alarm, but a statistical whisper so quiet it was almost lost in the digital noise. At the Vera C, Rubin Observatory, perched high in the Chilean Andes, a nightly processing pipeline flagged a minuscule deviation. The blue light from 3I, Atlas, when measured against 1,000 stellar standards, seemed just a fraction of a percent less blue. The anomaly was logged automatically, buried in terabytes of data, initially dismissed as a momentary fluctuation in Earth's atmosphere, a subtle calibration error in one of the telescope's sensitive detectors, or perhaps a wisp of high-altitude cirrus cloud drifting through the field of view. These things happen. Astronomy is the art of pulling a signal from an ocean of noise. You learn to ignore the ripples to focus on the tide. A few days later, a similar flag was raised by the Keck Observatory in Hawaii. An astronomer on duty, bleary-eyed from a long night of observations, ran the data again, checked the atmospheric models, and shrugged. The deviation was at the very edge of significance. It was a ghost in the machine, a phantom that would surely vanish with the next dataset exercised by the cleansing power of a larger statistical sample. But it didn't vanish. The phantom began to take on flesh. The whisper grew into a persistent, unsettling murmur. Across the world, the same subtle shift was being recorded independent of location, instrumentation, or weather. Frantic emails began to flash between continents. What was once a dismissible error in a single observation was now a pattern emerging from the combined gaze of humanity. The consensus, once a bedrock, started to show hairline cracks. The object was changing. We had all assumed 3I. Atlas was a static entity, a frozen snapshot of its home system. We believed we were watching a celestial artifact inert and unchanging as it glided through the warmth of our inner solar system. But this assumption, like so many before it in the history of science, was proving to be profoundly, fundamentally wrong. We weren't looking at a museum piece. We were watching something alive with dynamic, unpredictable physics. The shift began to accelerate the gentle drift, turning into a determined march across the electromagnetic spectrum. Week by week, the data pouring in from telescopes like Hubble and the JWST, which could stare at the object unimpeded by our planet's turbulent atmosphere, confirmed the impossible with terrifying precision. The peak of its reflected light, that beautiful spike in the blue wavelengths, was migrating. It was sliding inexorably toward the longer, redder end of the spectrum. The cool sapphire was fading, replaced by a pale aquamarine, then a muted cerulean, then a strange, sickly green. Within the astronomical community, a quiet panic began to set in. Whiteboards in university physics departments became canvases of frantic equations. Supercomputer clusters were tasked with running simulations day and night, trying to model a physical process that could account for such a rapid transformation. This wasn't supposed to happen. Our models of interstellar objects, based largely on the brief passage of Oumuamua and our understanding of our own comets, had no room for this. It was like watching a blue marble turn into a ruby while you held it in your hand. The implications were staggering. Finally, the moment of shocking, undeniable revelation arrived. It was no longer a subtle shift for spectrographs to debate. It was a change so profound you could almost see it with your own eyes. 3I, Atlas, was no longer blue. It was red, not the familiar dusty red of Mars or a rust-coloured asteroid, but a deep alien crimson, the colour of a smouldering ember. It was a raw, inorganic blush that spoke of violent chemistry and extreme physics. The messenger from the stars had changed its message mid-sentence. The initial clue that had formed the foundation of all our theories had not only been erased, it had been inverted. The entire scientific endeavour had to be reset to zero. The question was no longer, why was it blue? The question now screamed across the globe was, what in the universe is it doing? 3 primary hypotheses, each more radical than the last, were thrown into the intellectual arena battling for supremacy. The first, and perhaps most conservative, centered on a process we know well: sublimation. This is the engine that drives comets. As they approach the sun, surface ices turn directly into gas, bypassing a liquid state and erupt into space, creating the beautiful coma and tail. Perhaps the theory went 3I. Atlas had a layered onion-like structure. Its outer shell, the one we first saw, could have been a thin veneer of those hyper-volatile ices like frozen nitrogen that stay solid only in the deep freeze of interstellar space. This layer, reflecting blue light, was its interstellar winter coat. But as it plunged deeper into our system, the sun's warmth, even as far out as the orbit of Jupiter, acted as a celestial blowtorch. This fragile blue shell was being boiled away atom by atom, exposing a completely different layer of material underneath. This newly revealed substrate, the thinking went, must be rich in tholins, complex organic compounds that are notoriously reddish in colour. We see them on Pluto, on Saturn's moon Titan, and in the Kuiper belt. They are formed when simple molecules like methane and nitrogen are irradiated by ultraviolet light over cosmic timescales. So in this scenario, 3I, Atlas, was simply shedding its skin, revealing a more familiar sun-baked complexion beneath. It was a plausible, elegant explanation. But it had a problem: the speed. The color change was happening far too quickly and far too uniformly. For sublimation to strip a surface so perfectly and so fast, the object would need to be venting gas with enormous energy, producing a visible coma, a cloud of dust and gas around it. Yet our most sensitive instruments detected nothing. 3I Atlas remained a stark, solitary point of light. It was changing its fundamental nature without kicking up any dust. It was a silent, perfectly controlled transformation defying the messy, chaotic nature of cometary physics. This led to the second, more haunting hypothesis, a history of violence written on its surface by eons of cosmic radiation. Imagine this object adrift between the stars for millions, perhaps billions of years. During that immense journey, it was not alone. It was constantly bombarded by a rain of high-energy particles, cosmic rays shot out from distant supernovae and ravenous black holes. This relentless shower of radiation is an invisible cosmic acid capable of breaking down chemical bonds and fundamentally altering matter. Scientists propose that this endless bombardment had created a deep, weathered crust on the object, a thick mantle of radiation-damaged material that was intrinsically dark and red, much like the tholins in the first hypothesis. So, where did the blue come from? The theory suggested that in the final, coldest leg of its interstellar journey, just before it stumbled into our solar system's gravitational embrace, it passed through a small, dense pocket of interstellar gas. This encounter, however brief, would have been enough to plate its surface with a micro-thin layer of pristine frost like morning dew on a stone. This delicate crystalline coating reflecting blue light was the face it showed us upon its arrival. But our sun is a far more ferocious beast than the diffuse starlight of the void. As 3I Atlas drew closer, the sun's intense ultraviolet radiation and the powerful solar wind began a process of photosputtering. They weren't melting the frost, they were sandblasting it away, molecule by molecule. The delicate blue veneer was being systematically erased, revealing the ancient radiation-scarred heartwood beneath. This model was compelling. It accounted for the lack of a coma, as the sputtering process would release individual atoms, not clouds of dust. It also painted a vivid picture of the object's immense age and brutal history. Yet it, too, faced a challenge from the incoming data. The spectral signature of the new red surface didn't perfectly match the signature of any known tholin or radiation-damaged ice. There were strange absorption bands in the infrared, subtle dips and peaks in the light that hinted at a composition that was familiar yet fundamentally alien. The ingredients were recognizable, but the recipe was from another star. The data was more complex than the theory allowed. The red material wasn't just a simple weathered crust. It was something else, something stranger. And so the third and most profound hypothesis emerged from the growing confusion. It challenged our most basic assumption that the object was a uniform whole. What if 3I Atlas was not a single homogeneous body? What if it was a composite, a cosmic chimera with vastly different materials existing side by side? Perhaps the color change wasn't a surface effect at all. Maybe it was the result of a fundamental reorientation of the object itself. We knew it was tumbling, rotating on at least two different axes in a complex, chaotic spin, likely the result of a long-ago collision. This chaotic tumble is a gravitational gyroscope, and as the object interacts with the sun's gravity, its spin dynamics could be subtly changing. What if this gravitational torque was causing it to shift its orientation, to show us a completely different face? Imagine a celestial geode with a mundane, rocky blue-grey exterior that, when cracked, reveals a stunning interior of crimson crystals. Perhaps 3I Atlas had a blue hemisphere and a red hemisphere, two distinct geological provinces forged in the chaotic disk of a long-dead star. Upon its arrival, its orientation just happened to show us the blue side. But now, under the gentle, persistent influence of our sun's gravity, it was slowly, inexorably turning, revealing its other hidden nature. This was a breathtaking idea. It implied that the object was not just a messenger, but a library containing multiple chapters of its home system's history on a single body. But it was also, for now, pure speculation, a convenient narrative that fit the facts but had no direct proof. To prove it, we would need to see the color change correlate perfectly with its complex rotational period. We would need to see it flicker or present a mottled transitional appearance as it turned. And the data, while not contradicting the theory, was not yet clear enough to confirm it. The signal was still buried too deep in the noise: radical sublimation, deep radiation weathering, or a dramatic axial tilt. 3 competing stories, 3 different pasts for our enigmatic visitor. Each one pushed the boundaries of our planetary science. Each one raised more questions than it answered. If it was sublimation, why was it so clean and efficient? What unknown physics could allow a body to shed its skin so silently? If it was radiation damage, what specific material were we looking at that had a spectral fingerprint unlike anything in our vast cosmic catalogues? And if it was a two-faced, Janus-like world, how could such a bizarre dichotomy form? What kind of planetary formation process creates a world with 2 so drastically different hemispheres? Every established model for the behavior of small bodies in our solar system was failing the test. 3I Atlas refused to fit into any of our neat little boxes. It was behaving like a comet in its trajectory, an asteroid in its lack of a coma, and like nothing we had ever seen in its spectacular rapid transformation. The frustration and excitement in the scientific community were palpable. This single tiny point of light was rewriting the rulebook in real time, and it was still coming closer. Its journey was far from over. It had not yet reached perihelion, its point of closest, most intimate approach to our star. The sun's heat and radiation would only intensify. The gravitational stresses would only grow stronger. The forces that had already transformed it from a blue jewel to a red ember were about to be turned up to their absolute maximum. What would happen then? Would the red color deepen further, shifting toward the infrared, rendering the object invisible to our eyes? Would the process reverse itself, or would the increasing thermal and tidal stresses be enough to tear this object apart, completely spilling its ancient interstellar secrets into the void for us to see at last? The frantic race was on a desperate campaign to gather every possible photon, every scrap of data, before it whipped around the sun and began its long, lonely journey back out into the eternal night, perhaps taking the answer to its impossible riddle with it forever. For weeks, the global astronomical community had been locked in a state of profound and frustrating paralysis. The data streamed down from every mountaintop and orbital platform, a fire hose of information that told us everything and nothing all at once. We had measured 3I, Atlas's trajectory, with breathtaking precision, confirming its voyage from the cold, dark gulf between the stars. We had calculated its spin, a slow and steady tumble through the void, a cosmic gyroscope set in motion an eternity ago. Yet the central maddening paradox remained a question that echoed in every virtual meeting and late-night email chain. How could something born in the deep freeze of interstellar space, something that should be a pristine, icy blue, suddenly blush a deep, unsettling red? The existing models were failing, buckling under the weight of this contradiction. One theory would explain the initial blue hue by positing a surface of frozen nitrogen, but it could offer no mechanism for the abrupt transition. Another could produce a red surface with complex organics, but it couldn't account for why we first saw it as a brilliant cobalt. It was as if we were watching a ship at sea inexplicably change the color of its sails in the middle of its voyage. The feeling was one of hitting a wall, a barrier not of physics but of imagination. We were missing a fundamental piece of the puzzle, a key insight that lay just beyond our view. The answer, when it came, would not arrive with a thunderclap, but as a whisper from a million miles above the Earth. It came from an instrument designed not to look at fast-moving visitors, but to stare into the deepest, coldest, and oldest corners of the universe. The James Webb Space Telescope, its primary mirror, a magnificent golden honeycomb, had been turned towards our enigmatic guest. This was a gamble. Webb is an instrument of immense power, but also of delicate precision. Aiming it at a relatively small, dim object moving against the backdrop of stars is a supreme technical challenge. It's like trying to read the fine print on a spinning coin tossed across a football stadium using a telescope designed to photograph distant galaxies. The teams coordinating the observation worked for days, refining the pointing, calculating the lead time, ensuring the faint light from 3I, Atlas, would fall perfectly onto Webb's sensitive detectors. What they were hunting for was not a picture but a spectrum. They were letting the light from this interstellar wanderer pass through a sophisticated prism, shattering it into its constituent wavelengths. Within that rainbow of infrared light, they hoped to find a story, a chemical barcode written in the language of molecules. Every element, every compound absorbs and emits light at very specific frequencies, creating a unique pattern of dark lines and bright peaks. It is a fingerprint of matter itself. The initial data that came back was subtle, almost disappointingly so. The spectrum was faint, a fragile line graph buried in a sea of cosmic noise. At first, it just confirmed what we already knew. The broad spectrum colour was indeed now firmly in the red part of the visible spectrum, bleeding into the near-infrared, where Webb operates. There were no glaring, obvious signatures, no smoking gun that screamed its identity across the solar system. But one young postdoc, Dr. Aris Thorne, at the Max Planck Institute, refused to let it go. He couldn't shake the feeling that something was hiding in the data, a ghost in the machine. For 72 hours straight, fueled by coffee and sheer intellectual stubbornness, he and his team worked. They stacked the observation frames one on top of the other, digitally combining them to amplify the faint signal from the object. They developed new algorithms to subtract the background light of distant stars and the faint thermal glow of the telescope itself. Slowly, painstakingly, they were pulling a whisper out of a storm, and then they saw it. It wasn't a sharp, dramatic peak, but a series of broad, shallow and overlapping absorption bands. It looked messy, indistinct, like a watercolour painting left out in the rain. To an untrained eye, it was meaningless static. To a trained astrochemist, it was the most electrifying sight in the world. This was not the clean, sharp fingerprint of simple ices like water or carbon dioxide. This was the signature of complexity. It was the mark of large, heavy, carbon-rich molecules tangled together in a chaotic, intricate web. The computer models ran the signal against a vast library of known chemical compounds searching for a match. The program churned through thousands of possibilities from simple hydrocarbons to exotic minerals. And after hours of processing, it returned a result with a 98% confidence rating. The substance coating the surface of 3I, Atlas, was a complex organic polymer. A specific class of polymer that scientists have a special name for, tholins. The word itself, coined by the visionary Carl Sagan, comes from the Greek for muddy or hazy. But the reality is far more poetic. Tholins are the stuff of cosmic creation. You won't find them forming naturally on Earth today because our oxygen-rich atmosphere would instantly destroy them. Instead, they are born in places without oxygen, where ultraviolet light from a star can cook simpler molecules like methane and ethane. The radiation shatters these simple compounds and forces the fragments to reassemble into long, complex, sticky chains. We see them in our own solar system. They are what give Titan, Saturn's largest moon, its thick orange smog-like haze. They are the dark, reddish stains we see on the surface of Pluto and on many objects in the Kuiper Belt. They are in a very real sense a kind of primordial clay, the raw material from which the more complex molecules of life might ultimately be assembled. And now we had found them clinging to an emissary from another star, but this discovery, as monumental as it was, solved one mystery only to create a deeper one. If 3I, Atlas, was covered in red tholins, why on earth did we first see it as blue? The answer to that question required another leap of insight, a connection between two seemingly unrelated data sets. The teams went back to the earlier observations, the ones that measured the cloud of gas, the coma that had first classified this object as a comet. At the time, the composition of that gas was puzzling. It contained the usual suspects like carbon monoxide, but it also contained an unusually high concentration of molecular nitrogen. On its own, this was a minor curiosity. But when combined with the discovery of tholins, it became the final, crucial piece of the puzzle. A new, breathtakingly elegant picture began to emerge. Imagine 3I, Atlas, as it drifted for untold eons through the crushing cold of interstellar space, a place far colder than our own distant Kuiper Belt. In that profound freeze, even nitrogen, a gas on Earth, would condense and fall like snow, blanketing the object in a thin, fragile crust of brilliant blue-white ice. This was the object we first saw, a pristine blue snowball, perfectly preserving whatever lay beneath. It was a sealed message in a bottle thrown from the shores of another sun. Then we watched as it drew closer to our star. The gentle warmth of the sun, barely perceptible to us, was like a celestial blowtorch to that delicate nitrogen frost. As 3I, Atlas, crossed a specific temperature threshold, a point we now call the nitrogen frost line, that icy crust didn't melt, it sublimated. It went directly from a solid to a gas, erupting from the surface in a gentle, almost invisible puff. This was the outgassing we detected. This was the faint coma that made us call it a comet. It was not a violent eruption like we see from our own comets, belching water vapor and dust. Instead, it was a quiet, ghostly exhalation, a celestial shedding of skin. As that shimmering blue veneer of nitrogen ice vanished into space, it unveiled what had been hidden for millions, perhaps billions of years. The true face of 3I, Atlas, a surface stained a deep, dark, organic red. A landscape painted with the raw chemistry of another world. The color shift was not a chemical reaction happening times on times the surface. It was the surface itself being revealed. We hadn't witnessed a change. We had witnessed an unveiling. This revelation was staggering, fundamentally reframing our entire perspective on this visitor. It was no longer just a rock or a simple comet. It was a layered object, a cosmic geode with a complex hidden geology. And the composition of those tholins, teased from the faint light by Webb's golden eye, told an even more profound story. They were not identical to the tholins we see on Pluto or Titan. The specific absorption bands in the infrared spectrum were shifted subtly different, indicating a unique chemical recipe. These alien polymers contained a higher ratio of nitrogen-bearing compounds, suggesting they were formed in a protoplanetary disk far richer in nitrogen than our own was during its formation. It was a direct physical clue about the chemical environment around its parent star. We were for the first time in human history performing a chemical analysis of the building materials of another solar system. This wasn't theoretical anymore. It wasn't a simulation. It was real. We were holding a piece of it in our hands, or rather in the focused beam of our telescopes. The object passing through our backyard was a time capsule carrying the frozen blush of a creation event that happened light years away and eons ago. The red color was the color of its ancient history, a history that had been protected under a layer of blue ice until its fateful encounter with our Sunday. The entire mystery had been inverted. The question was no longer, why did it turn red? The question was now a set of far more profound and thrilling inquiries. What kind of star system could create such an object? A system with a different chemical budget, a different evolutionary path. How long did it travel, cocooned in its nitrogen shell, before stumbling into our path? And the most tantalizing question of all, these complex nitrogen-rich organic molecules, this primordial clay baked by the light of a distant star, what else might they have helped to build in their home system? The discovery had not provided a final answer. Instead, it had flung open 1,000 new doors, revealing a universe more complex, more varied, and more astonishingly creative than we had ever dared to imagine. 3I, Atlas, was no longer just an object of study. It had become a messenger, and its message, written in the colors of ice and organic haze, was only just beginning to be deciphered. And so the truth of the color shift settles upon us, not as an ending, but as a staggering new beginning. The simple observation of blue turning to red has been ripped open, revealing a living process, a dynamic chemical engine firing up on the surface of 3I, Atlas. This is not a passive coat of paint applied in the deep freeze of interstellar space billions of years ago. It is an act of creation happening right now before our very eyes. As the sun's faint initial warmth began to touch its frozen surface, something stirred. The simple ices we expected, nitrogen, methane, carbon monoxide, were not merely sublimating into gas. They were being shattered, their fundamental atomic bonds broken apart by the relentless wash of ultraviolet radiation from our star. Imagine a celestial forge, a microscopic anvil where sunlight is the hammer. Each photon strikes with unimaginable energy, liberating carbon, hydrogen, and nitrogen atoms from their icy prison. Once freed, these reactive elements do not simply drift away into the void. They begin a frantic, chaotic dance on the surface, a primordial ballet of recombination. They collide, they bond, they form new and ever more complex structures. Simple molecules give way to more elaborate chains, which then curl into intricate rings. This is the birth of tholins, the complex carbon-rich organic molecules that stain the outer solar system from the hazy atmosphere of Titan to the dark plains of Pluto. But here on this traveler, we are witnessing the process unfold in real time. We are watching a pristine blue-hued body from another star system develop a ruddy organic skin as it awakens in the heat of our own. The deepening red is not a color, it is a symptom of chemistry. It is the blush of a world coming alive with the very building blocks of biology. This single transformative fact shatters our perspective, forcing us to look beyond this one lonely object and ask a far more profound question. If it can happen here on this random shard of a distant solar system, where else is this process unfolding across the cosmic dark? We are forced to reevaluate what an interstellar object truly is. For decades, we imagined them as inert messengers, time capsules of rock and ice, geologically interesting but chemically frozen. 3I, Atlas, suggests they are something more. They are not just messages in a bottle. They are potentially the bottles, the ingredients, and the recipe all in one. They are traveling laboratories carrying the raw materials for prebiotic chemistry from one star system to the next. Consider the sheer scale of this possibility. Our galaxy, the Milky Way, is not a static collection of stars. It is a dynamic, churning ecosystem. For every star you see, astronomers now estimate there could be thousands, perhaps even millions of unbound nomadic worlds like 3I, Atlas, ejected from their birth systems and sailing silently through the interstellar gulf. Trillions upon trillions of them, a ghost population of objects crisscrossing the galaxy over billions of years. Most will travel forever in the frigid dark, their chemical potential locked in ice, but some, by pure chance, will do exactly what 3I, Atlas, is doing now. They will wander into the warm, life-giving vicinity of a star. As they approach, their surfaces will ignite with the same organic chemistry we are now observing. They will begin to manufacture tholins, brewing a complex soup of prebiotic molecules, and as they swing around that star, they will inevitably shed material. Dust, gas, and ice, all now enriched with these freshly synthesized organics, will trail behind them in a vast, invisible plume. A star's gravity is an anchor, and its solar wind a sculptor, ensuring that this visiting object does not leave without paying a toll, leaving behind a portion of itself. This is a galactic delivery service on an unimaginable scale. It suggests that the raw ingredients for life are not exclusively homegrown, cooked up in the primordial oceans of a young planet. Instead, they may be constantly delivered from the interstellar medium, sprinkled across nascent solar systems by an endless parade of wandering comets and asteroids. This idea radically alters our understanding of our own origins. We've long wondered how Earth, a sterile ball of rock and water 4.5 billion years ago, made the spectacular leap from simple geology to complex biology. How did the first amino acids, the first nucleotides, form from the chaotic chemical inventory of the early planet? Perhaps the answer wasn't just in our oceans or our atmosphere. Perhaps the key ingredients arrived from beyond. Imagine a young Earth bombarded by a hail of interstellar visitors like 3I Atlas. Each impact would deliver not just water and ice, but a payload of complex, energy-rich organic molecules ready-made to participate in the first tentative steps toward life. These tholins raining down into the warm primordial seas could have provided the crucial head start to the essential framework upon which life's more complex machinery was built. 3I, Atlas, then is more than just a curiosity. It might be a direct glimpse into our own planet's distant past, a tangible example of the very process that may have seeded Earth with the potential for life. But this revelation immediately spins off a new, more complicated mystery. If 3I, Atlas, is a product of its home, a fossilized piece of the planetary nursery where it was born, then its unusual composition is a set of clues. Its specific blend of ices and silicates is a fingerprint telling us something profound about the star system it came from, and that fingerprint is perplexingly strange. Our own solar system's comets born in the Kuiper Belt and the Oort cloud have a relatively predictable chemical makeup. They are rich in water ice. But the initial spectra from 3I, Atlas, suggest it is surprisingly water-poor. Instead, it seems to be dominated by more volatile ices like nitrogen and carbon monoxide compounds that freeze at much lower temperatures. This small detail is a colossal clue. It implies that 3I, Atlas, was likely formed in a region of its own protoplanetary disk that was far, far colder than the birthplace of our own comets. It whispers of a home environment of unimaginable frigidity, perhaps orbiting its parent star at a much greater distance than our own Kuiper Belt, or perhaps orbiting a star that was itself much cooler and dimmer than our Sunday. A red dwarf, for instance. Or maybe it wasn't about the star at all. Perhaps the molecular cloud from which its solar system condensed was simply different from our own, unusually rich in nitrogen and carbon compounds. We are like cosmic detectives holding a single alien stone and trying to reconstruct the geology of an entire world we have never seen. The proportions of its elements, the isotopic ratios within its molecules, every photon of light reflected from its surface is a piece of a puzzle from a star system we may never identify. Does the prevalence of nitrogen ice explain why its organic chemistry is so potent? Nitrogen is a cornerstone of life as we know it, a critical component of every amino acid and every strand of DNA. A delivery system that is naturally rich in nitrogen-based organics could be a profoundly effective vector for seeding life. This forces us to consider the sheer diversity of planetary formation across the galaxy. We have a tendency to view our solar system as a template, a standard model for how planets are made. 3I, Atlas, violently argues against that notion. It suggests that out there, among the billions of other stars, planetary systems are forming with wildly different chemical inventories. Some may be water-rich, like ours. Others may be carbon-heavy or nitrogen-dominated, or rich in sulfur. Each of these unique chemical starting points would lead to the formation of entirely different kinds of comets and asteroids. And if these objects are the galaxy's itinerant seed spreaders, then the seeds themselves are not all the same. The prebiotic soup delivered to a young planet might have a completely different flavor depending on which interstellar wanderers happen to pass through its neighborhood. This paints a picture of astrobiology that is infinitely more complex and exciting. The pathway to life might not be a single narrow road, but a vast branching network of possibilities, fueled by a diverse chemical inheritance from across the galaxy. And this leads us directly to the heart of the great debate that now rages in laboratories and observatories around the world. We see the red color, we see the tholins forming. We understand that 3I, Atlas, represents a vehicle for delivering organic molecules. But what precisely is being delivered? Is this traveler truly a seed of life, or is it merely a fascinating but ultimately sterile chemical curiosity? On one side of this debate are the astrobiologists, who see this object as a harbinger of profound optimism. They argue that tholins are not just random organic gunk. Laboratory experiments which simulate the conditions on icy bodies have shown that when tholins are dissolved in liquid water, they spontaneously break down to form amino acids, the fundamental building blocks of proteins. They can also form nitrogenous bases, the informational rungs on the ladder of DNA and RNA. From this perspective, 3I Atlas is a nearly complete starter kit for biology. It carries the complex precursors shielded within its icy matrix across the lethal vacuum of space. Upon arriving at a suitable world, a rocky planet with liquid water like early Earth, it delivers its payload upon impact. The heat of the collision would melt the ice, releasing the tholins into the water, and in that moment, the final crucial step of prebiotic chemistry could occur almost instantaneously. It's a compelling, almost romantic vision, a galaxy fertilizing itself with these interstellar comets, acting as cosmic pollinators, dusting young planets with the essential ingredients and kick-starting the long journey toward life. For proponents of this view, the red color of 3I, Atlas, is the color of promise. It is the hue of Genesis, a symbol that the universe is hardwired to create the building blocks of biology wherever conditions allow. It suggests that the emergence of life on Earth may not have been a 1 in a trillion fluke, but the predictable outcome of a universe awash with such ingredients. But on the other side of this intellectual divide stands a healthy and necessary scientific skepticism. These researchers urge caution. While tholins are undeniably complex, they argue complexity is not the same as biological relevance. The universe is full of complex chemistry that has nothing to do with life. The red dust on 3I, Atlas, might be little more than a sterile tangled asphalt, a chemical dead end. Just because laboratory experiments can coax amino acids from tholins under controlled conditions doesn't mean it happens efficiently or at all in the chaotic aftermath of a comet impact. Furthermore, they point to the problem of chirality, the handedness of molecules. Life on Earth exclusively uses left-handed amino acids and right-handed sugars. A random chemical process like the one creating tholins on 3I, Atlas, should produce an equal mixture of both left and right-handed versions. Bombarding a planet with this 50/50 mix known as a racemic mixture might actually hinder the origin of life rather than help it, creating a chemically confused environment where the specific lock and key mechanisms of biology cannot gain a foothold. For these scientists, 3I, Atlas, is an object of immense chemical and geological importance, but its link to astrobiology is speculative at best. It is a stunning example of exotic non-terrestrial chemistry, a testament to the universe's creativity. But to call it a seed of life is a leap of faith, a projection of our own biological hopes onto an object that may simply be a very interesting, very red rock. They remind us that the jump from even the most complex amino acids to a self-replicating, metabolizing organism is a chasm of such staggering width that we have not even begun to map its edges. Delivering the bricks does not mean you have built a cathedral. The tholins might be nothing more than a pile of raw materials with no architect to assemble them. This sober-minded perspective is crucial. It keeps the investigation grounded, preventing us from drawing conclusions that the evidence cannot yet support. It complicates the beautiful, simple story of a red comet bringing life to the stars, reminding us that the universe is rarely that simple or that generous. This deep division of opinion reveals the true significance of 3I, Atlas. It has transcended being a mere astronomical object and has become a philosophical battleground. It is a mirror reflecting our deepest hopes and our most rigorous scientific doubts about our place in the cosmos. Is life a cosmic imperative, a natural outcome of chemistry that the galaxy actively cultivates and spreads? Or is it a fragile, improbable accident, a lucky chemical roll of the dice on one small planet in a universe that is otherwise beautiful but barren? This single reddish point of light carries the powerful weight of these monumental questions. Every new piece of data we gather from it could tip the scales of this grand debate. And as we continue to watch, pushing our instruments to their absolute limits, a new wrinkle is beginning to emerge. The story, it seems, is not finished. The simple explanation that ultraviolet radiation is creating tholins on the surface is beginning to look incomplete. As 3I, Atlas, gets closer and our measurements become more precise, a faint but persistent anomaly has appeared in its light spectrum. It is a subtle absorption feature, a sliver of light being absorbed by a material that does not perfectly match the spectral fingerprint of any known tholin mixture we can create in a lab. It is something else, something unexpected hiding within the overwhelming redness. This is the nature of discovery. An answer once found rarely closes the book. More often it reveals that we have been reading the wrong chapter all along. The red color told us a story of organic creation on the surface, a story of prebiotic potential being unlocked by the Sunday. It was a beautiful, compelling narrative that expanded our vision of the galaxy. But this new unexpected signal, this quiet ghost in the machine, does not fit that narrative. It hints at a deeper complexity, another layer of the mystery we had not even conceived of. The color shift, the great revelation of this encounter, has suddenly become just the first clue in a much larger puzzle. It raises a disquieting possibility. What if the reddening of 3I, Atlas, is not just one process but two or three. What if the tholins are only part of the story? This new spectral feature speaks of a different kind of chemistry, or perhaps a different physical process entirely. Is there a mineral on the surface, something from its home system that is reacting to the heat in a way we don't understand? Or is the change coming not from the surface, but from deep within? As the object warms, could internal pressures be forcing some exotic primordial material from its core to its surface, altering its color and composition in a way that mimics but is not identical to the formation of tholins? The simple interpretation is fracturing. The journey of 3I, Atlas, has just become infinitely more complicated and infinitely more tantalizing. The red hue is no longer a simple answer. It is now a compound question, pointing toward an even more alien truth, buried just beneath the surface, undefined. And so the paradox of 3I, Atlas deepened with every passing hour. All the data we had so painstakingly gathered from the most powerful observatories on Earth and in orbit seemed only to contradict itself. We had tracked its trajectory, a clean hyperbolic arc, proving its journey from the cold between the stars. We had measured its initial color, that impossible crystalline blue, a hue so pure it spoke of conditions colder and cleaner than anything in our own solar system. Then we had watched stunned as it performed its grand celestial metamorphosis, blushing from that ethereal blue into a deep organic red. The pieces of the puzzle were all there, scattered on the table of science. The spectrographs showed the faint, fleeting signatures of gases, a whisper of a coma, where none was expected for an object so far from the sun. The light curves hinted at a surface in flux, its brightness subtly and erratically shifting, as if the object were shrugging off a dusty coat. The thermal readings were a quiet enigma, suggesting a surface reacting to our star's distant warmth in a way that defied simple explanation. Each new observation was a clue, but a clue that pointed in a dozen different directions at once. Was it merely a strange asteroid, its surface minerals reacting to faint solar radiation in some unknown way? Or was it a comet of an entirely new class, its icy heart stirring far earlier than our models had ever predicted? The competing hypotheses were a battlefield of brilliant ideas. One team proposed that the blue color came from incredibly fine-grained, almost nanoscale dust, an exotic silicate that scattered blue light, which was then blown away by the solar wind to reveal a redder core beneath. It was an elegant idea, but it couldn't fully account for the speed of the transition or the specific gases detected. Another group argued for a surface of solid nitrogen, a frozen sea that once it began to sublimate, exposed a rocky, carbon-rich interior. This aligned better with the gaseous emissions, but the thermal models struggled. Solid nitrogen should have boiled off far more violently in a brilliant outburst, not this gentle, progressive transformation. Every theory we constructed, every model we built, captured one or two facets of the mystery, but none could encompass the whole. The object in our telescopes remained a ghost, a beautiful contradiction that refused to give up its secrets. We were missing something fundamental. We were missing the key that would unlock not just one piece of the puzzle, but reveal how all the pieces fit together in one breathtaking, coherent picture. That key would not be found by looking through a telescope alone. It would be forged in the digital heart of our most powerful supercomputers. Here, in virtual universes governed by the laws of physics and chemistry, scientists could finally put all the disparate clues on trial together. They could build a digital twin of 3I, Atlas, feeding it every scrap of data, its velocity, its spin, its distance from the sun, its thermal profile, and the precise spectral fingerprints of its transformation. They could bombard this virtual object with simulated sunlight, tweak its chemical composition atom by atom, and run time forward, watching for that one sequence of events, that one unique recipe that would perfectly replicate the 4-1, chameleon-like shift we had witnessed across the gulf of space. For months, these simulations ran, producing a universe of failures. Digital comets that remained stubbornly blue, asteroids that started red and stayed red. Objects that disintegrated too quickly or didn't react at all. Each failure was a lesson, narrowing the field of possibilities, but the central mystery remained unsolved. until one simulation running on a machine capable of quadrillions of calculations per second began to behave differently. It didn't just match one or two data points, it began to reenact the entire story flawlessly. On the screen, a small, spinning world of impossible blue glimmered against the black. The simulation began, and as the virtual object arced closer to its digital sun, a change began to ripple across its surface. It was a slow, deliberate peeling away of that blue layer, not in a chaotic explosion, but in a controlled, almost biological-looking cascade. Beneath it, a darker, grayer substrate was revealed, and then, as the simulation continued, something extraordinary happened to that newly exposed layer. Under the persistent wash of virtual ultraviolet light, it began to blush. Subtly at first, then, with accelerating speed, it transmuted into a deep, rich, organic red. The team watched breathless as the final light curve and spectral data from the simulation flashed on screen. It was a perfect match, a one-to-one correspondence with reality. They had found it. They had found the key. What they had uncovered was not a single event, but a multi-stage, interconnected chemical symphony, a process more complex and more beautiful than we had ever dared to imagine. The initial blue the simulation revealed was not common water ice or even the nitrogen we had suspected. It was a fragile, crystalline frost of something far more exotic and volatile, a thin veneer of supercooled carbon monoxide and dinitrogen monoxide ice, mixed with trace amounts of methane clathrates. These are substances that can only exist as a solid in the truly abyssal cold of interstellar space, far from the gentle warmth of any star. Formed over eons in a dark molecular cloud, this delicate frost was the object's cryogenic seal, its shield of preservation. This specific mixture of ices, when frozen to near absolute zero, forms a crystalline structure that is fantastically efficient at scattering short-wavelength blue light while absorbing red and yellow. The impossible blue of 3I, Atlas, was the colour of the interstellar void itself, a pristine glaze from the coldest nursery in its parent star system. As the object drifted into our solar system, it encountered a force it had not felt for millions, perhaps billions of years, the faint but persistent pressure of sunlight. For this ultra-volatile frost, even the distant sun was a furnace. The first stage of the transformation began. The carbon monoxide, the most delicate of the ices, started to sublimate, turning directly from a solid into a gas. This wasn't a violent eruption like we see on our own comets. It was a gentle but inexorable fizzing, a cosmic evaporation that lifted the blue veil atom by atom. This slow, steady sublimation perfectly explained the faint, almost undetectable coma that had puzzled astronomers. It also explained the erratic flickering in the object's brightness, as patches of the frost gave way, exposing the darker material beneath. We were not watching a geological event. We were watching the object shed its ancient interstellar skin. We were witnessing the moment its billion-year alarm clock set by the physics of its home system was finally triggered by our star. This sublimation cascade was only the first act. The true revelation lay in what was uncovered. As the blue frost vanished into space, it did not reveal a dead rocky core. Instead, it exposed something far more profound, a deep mantle of primordial organic material. This wasn't the complex reddened stuff we see on comets in our own solar system. This was the raw material, the starting point. The simulations showed a surface of greyish, almost colourless compounds, simple hydrocarbons, ammonia, and water ice all bound together in a porous, unprocessed matrix. These were the fundamental building blocks of biochemistry, preserved in a chemically unaltered state by the protective blue frost that had encased them since their formation. You are seeing the object as it was born, a perfect time capsule carrying the original chemical inventory from a long-dead protoplanetary disk. For a breathtaking moment in its journey, 3I, Atlas, was a naked ghost, its primordial heart exposed to the cosmos for the very first time. But this state of vulnerability was fleeting. This is where the final and most spectacular act of the drama unfolded. The departure of the volatile blue ice did more than just expose the organic layer beneath. It initiated its rapid and irreversible transformation. Two processes working in perfect concert began the reddening. First, the ultraviolet radiation from our sun, no longer blocked by the reflective blue frost, could now strike the exposed organic surface directly. This high-energy light is a powerful engine for chemistry, shattering the simple molecules and providing the energy for them to reform into something new, something more complex. The simple chains of hydrocarbons and ammonia began to link together, polymerizing into longer, more intricate structures. This process on its own would slowly redden the surface over thousands of years, but the transformation of 3I, Atlas, happened in mere weeks. There had to be something else at work, an accelerator. The simulation provided the final stunning answer. The very gases being released by the sublimating frost were acting as a powerful catalyst. The gaseous carbon monoxide in the presence of UV radiation was dramatically speeding up the polymerization of the surface organics. It was a perfect self-contained chemical engine. The evaporation of the outer layer was actively triggering the transformation of the layer beneath. The simple, colorless molecules were cross-linking, tangling, and growing, forming a complex carbon-rich molecular web. This new material is what astronomers call a tholin. Tholins are not one specific molecule, but a thick, sticky, reddish-brown goo of incredibly complex organic polymers. They are found throughout the outer solar system on the surfaces of Pluto, Triton, and many other distant worlds. They are, in essence, a form of cosmic rust, the end product of simple organics being irradiated for long periods of time. On 3I, Atlas, however, we were not seeing the end product. We were watching the factory floor itself, witnessing the creation of tholins in real time, catalyzed and accelerated by the object's own unique chemistry. The blue to red shift was therefore not just a color change, it was the signature of a profound chemical awakening. It was the story of a pristine object preserved for eons in the sterile deep freeze of space finally being activated by the light of a new star. The blue was the color of its preservation, the red was the color of its reaction. This definitive explanation, born in a supercomputer and confirmed by reanalyzing every shred of observational data, solidified the identity of 3I, Atlas. This was no random space rock. It was not merely a comet. It was something far more significant. We had intercepted a perfectly preserved, chemically active time capsule from the birth of another star system. The gases that sublimated were the last exhalation of its home nebula. The organic mantle was the raw clay from which its native planets were built. And the color change was our first privileged glimpse into the processes of alien biochemistry unfolding live across our cosmic backyard. The implications are almost overwhelming. We have always speculated that the building blocks of life were forged in space and delivered to young planets by comets and asteroids. We call this theory panspermia, the seeding of life from world to world, from star to star. It has remained a powerful but unproven idea. But in 3I, Atlas, we have found the smoking gun. Here is an object born in a completely different stellar neighborhood that not only carries all the necessary prebiotic ingredients, but possesses a built-in mechanism to transform them into complex organic polymers the moment it enters the life-giving warmth of a star system. It is a perfect delivery vehicle, a planetary starter kit assembled in one corner of the galaxy and shipped to another. Its journey to our sun was not just a passage, it was the final step in a cosmic recipe that began billions of years ago and light years away. We were no longer just astronomers observing a celestial body. We had become witnesses. We were watching the fundamental processes of creation, the very first rungs on the ladder that might, under the right circumstances, lead to biology. The reddish tholins forming on its surface are thought to be critical precursors for amino acids and nucleotides, the very foundation of life as we know it. This object is a message written in the language of chemistry telling us that the ingredients for life are not unique to our small corner of the universe. It tells us that other solar systems are built from the same primordial starter dough. And it demonstrates a powerful, elegant mechanism for processing that dough into something much more interesting. Now, as we watch 3I, Atlas, continue its journey, its new red coat gleaming in the sunlight, we are forced to confront a question that resonates deeper than any before. If these organic-rich messengers are flitting between the stars, seeding every nascent planetary system they encounter, then just how common is the raw potential for life throughout the galaxy? What does this wandering world builder tell us about our own origins and about the odds of finding something wondrous in the oceans of worlds yet to be discovered. What then are we left with as the faint signal of 3I? Atlas fades forever into the black. We are left with the ghost of a memory, the echo of a profound cosmic question that arrived unannounced and departed without a final answer. Our encounter was fleeting, a frantic scramble to capture a shadow as it drifted through our sunlit home. We aimed our most powerful eyes at this solitary traveller, this emissary from an unknown star, expecting to catalogue another fragment of a familiar story. We anticipated a playbook written in the same chemical language as our own asteroids and comets, a comforting confirmation that the recipe for worlds was universal, a standard model repeated across the galactic expanse. Instead, this silent wanderer performed a startling act of cosmic theatre right before our eyes, a transformation so profound it has shaken the very foundations of planetary science. It forced us to tear up the script we thought we understood. The journey to comprehend 3I, Atlas, was not merely a process of observation, it was an intellectual odyssey, a humbling lesson in cosmic diversity. We watched, we theorized, and we were proven wrong again and again. We began with a puzzle box, a tiny faint speck of blue, a colour so unexpected, so alien to the typical dusty red hues of our own outer solar system that it immediately signalled we were dealing with something extraordinary. This was not just another rock. Was it, as some first proposed, the naked iron core of a shattered protoplanet, a relic of some ancient violent cataclysm in its home system, a world torn asunder, its metallic heart flung into the interstellar void to wander for eons? The data seemed to fit, and for a moment we held in our minds the image of a system far away that suffered a catastrophe of unimaginable scale. We were reading the autopsy of a dead world. Then, as if to mock our premature conclusions, the object began to change. Its cool, distant blue began to warm, to shift, to deepen into a rich, unmistakable red. This was no static, dead fragment of iron. This was something active, something dynamic. Something was happening out there millions of kilometers away as the gentle, warming breath of our own sun touched this long-frozen visitor. The transformation was our paradigm shift. It was the moment a simple object became a profound enigma. The reddening of 3I, Atlas, was not just a change in its spectral signature, it was the universe handing us a Rosetta Stone inscribed with the chemistry of a place we may never see. This chromatic metamorphosis became the central mystery, the clue that unraveled all our simple assumptions and opened up a universe of spectacular possibilities. We were no longer just observing an object, we were witnessing a process. The sun's energy, a celestial blowtorch applied with surgical precision, was likely peeling back the object's outer layers, revealing what lay beneath. Imagine a chrysalis traveling for millennia through the absolute zero of deep space, its outer shell hardened and scoured by relentless cosmic radiation. Then, upon entering the warmth of our star system, it begins to stir. The outer casing, perhaps made of exotic ices like solid nitrogen or carbon monoxide, sublimates away, turning directly from a solid into a gas. This process, this shedding of its ancient space-weathered skin, could have been what we were seeing. The blue colour might have been the signature of that primordial irradiated frost, while the emerging red was the true face of the object beneath a surface rich in complex organic molecules known as tholins. These are not simple compounds. Tholins are the stuff of astrobiological dreams, sticky reddish-brown molecules forged when ultraviolet light irradiates simpler compounds like methane and ethane. On Saturn's moon Titan, they rain from the hazy sky, coating its surface in a dark organic sludge. In the outer reaches of our own solar system, they paint distant Kuiper belt objects in shades of deep red. Finding them on 3I, Atlas, suggests that the chemical factories that produce these precursors to life are not unique to our corner of the cosmos. The visitor from afar was carrying the very same palette of colours, the very same organic ingredients that we find on the fringes of our own planetary family. It was a stunning moment of connection, a realization that the fundamental building blocks for worlds, and perhaps for life itself, are being cooked up in the frigid darkness around other stars following similar recipes. This visitor was not entirely alien after all. It was a distant cousin formed from a shared galactic inheritance of dust and gas. It carried a message of profound reassurance. The chemistry that led to us may not be a cosmic fluke. Yet the story it told was also one of startling difference. The sheer speed and totality of its color shift hinted at a composition subtly yet critically distinct from anything we know. The specific nature of the ices that vaporized the precise composition of the organic mantle they revealed, these are the fingerprints of its home environment. The delicate balance of chemicals in a protoplanetary disk is exquisitely sensitive to the type of star it orbits, its distance from that star, and the presence of other massive planets stirring the pot. The vibrant blush of 3I, Atlas, was therefore more than just a chemical reaction. It was a core sample, a geological survey of its birthplace. It was a testament to a different path of planetary formation. Perhaps its parent star was hotter or cooler than our Sun. Perhaps its home system was richer in certain elements, a unique stellar nebula that cooked up its planetary ingredients with a different spice blend. This single object in its brief passage demonstrated with breathtaking clarity that the galaxy is not a monolith. It is a mosaic of countless chemical provinces, each with its own distinct environmental history, each producing its own unique catalogue of worlds. We had assumed a degree of uniformity, but 3I, Atlas, was a vibrant, screaming testament to cosmic individualism. It shattered the illusion that other solar systems are simply copies of our own. They are unique ecosystems, each with the potential to generate planetary surfaces and atmospheric compositions wildly different from anything we have ever imagined. This realization carries with it one of the most profound implications of our encounter. If the raw materials for planets are so varied from one star system to the next, what does that mean for the possibilities of life elsewhere? We search for extraterrestrial life based on the one example we have: life on Earth. We look for worlds with liquid water, with carbon-based chemistry, with atmospheres we might recognize. We are, in a sense, looking for a reflection of ourselves in the cosmic mirror. But 3I, Atlas, serves as a powerful reminder that the universe may have no obligation to repeat itself. Its unique chemistry suggests that the building blocks of astrobiology, the very starting materials from which life might emerge, could be fundamentally different in other systems. Could life arise from a different solvent than water? Could it be based on a different molecular backbone than carbon? The reddening of this one small object opens the door to these breathtaking questions. It forces us to broaden our imagination, to consider that life, if it exists elsewhere, might be built from a chemical toolkit so alien we might not even recognize it at first. 3I, Atlas, wasn't just a rock, it was a philosophical provocation, a challenge to the very core of our astrobiological assumptions. It whispered a secret as it passed by: the universe is far more creative, far more diverse, and far stranger than we have ever dared to believe. And so, we are left standing on the shore of a cosmic ocean, having watched a single mysterious bottle wash ashore and then be reclaimed by the tide. We were not ready for it. Our nets were not wide enough, our instruments not fast enough to truly capture and analyze its message before it was gone. We are haunted by the questions it left in its wake, questions that now fuel a revolution in astronomy. The fleeting passage of 3I, Atlas, and Oumuamua before it has ignited a fervent global quest to ensure that next time we will be prepared. We can no longer be passive observers waiting for luck to send another messenger our way. We must become active sentinels, vigilant guardians of our solar system's frontiers, ready to intercept these travelers and unlock the secrets they carry. This is the legacy of 3I. Atlas, it has transformed interstellar objects from theoretical curiosities into the most vital and sought-after targets in modern astronomy. They are no longer phantoms, they are tangible priorities. Across the globe, a new generation of eyes is turning toward the sky designed specifically for this grand purpose. The Vera C, Rubin Observatory, perched high in the Chilean Andes, is poised to become our planet's ultimate watchdog. When it begins its decade-long survey, it will scan the entire visible sky every few nights with unprecedented depth and speed. Its vast digital eye will create the most detailed motion picture of the universe ever assembled, cataloging billions of objects. Within this torrent of data, it is expected to find not one or two, but dozens of interstellar visitors every single year. It will be our early warning system, our celestial tripwire. The Rubin Observatory will not just discover these objects, it will spot them far earlier in their approach, giving us precious weeks, months, or even years to prepare. That is time we have never had before. It is the time needed to mobilize the world's greatest observatories, to pivot our most powerful instruments, and to focus their combined might on these fleeting guests. When that alarm sounds, we will be ready to respond with an arsenal of analytical tools beyond the dreams of earlier astronomers. The James Webb Space Telescope, our magnificent infrared eye in the cosmos, can be trained on these targets to perform detailed spectroscopy. It can dissect the faint light reflecting from their surfaces, breaking it down into a barcode of chemical signatures. It will be able to tell us not just that an object is red, but precisely which complex organic molecules are responsible for that color. It will hunt for the telltale signs of water ice, carbon dioxide, methane, and other compounds, creating a detailed chemical inventory that will tell us the story of the object's origin. We will move beyond inferring composition to measuring it directly. We will build a library, a catalogue of chemistries from other star systems. Each new visitor will be a new chapter, adding to our understanding of the galactic distribution of the elements that are essential for planets and for life. We will become cosmic cartographers, mapping not the geography of stars, but the chemical continents of their nascent planetary systems. Beyond observation from afar, the ultimate dream is now being sketched out in engineering labs and theoretical workshops, a mission of interception. Imagine a dedicated spacecraft, a rapid response probe, waiting in a state of hibernation for the Rubin Observatory to sound the alert. Upon detection of a new interstellar visitor with a favorable trajectory, this probe would awaken. Its engines would fire, propelling it on a high-speed chase to catch up with the traveler, to fly alongside it, perhaps even to send a smaller impactor to kick up a plume of surface material for direct analysis. A mission like the conceptual interstellar probe designed to leave our own solar system is already pushing the boundaries of propulsion technology. Adapting this vision into an intercept mission is a monumental engineering challenge, requiring unprecedented speed and navigational autonomy. Yet it is a challenge that we are now compelled to undertake. The scientific prize is simply too great to ignore. To be able to touch, to taste, to analyze a piece of another solar system in our own laboratories would be a discovery on par with finding life on Mars. It would transform planetary science from a discipline of remote observation into a hands-on, tangible exploration of galactic real estate. This is the future that 3I, Atlas, has helped to inspire. A future of vigilance, of rapid response, and of bold exploration. We stand at a remarkable threshold, transitioning from a species confined to studying its own cosmic backyard to one capable of sampling the vast wild garden of the galaxy. Every star you see in the night sky is a potential source for one of these messengers. Around those stars are swirling disks of gas and dust, planetary nurseries churning out worlds with chemistries we can't yet imagine. Some of those systems are violent and chaotic, flinging their infant planets and comets out into the abyss. Those orphans then travel in silence and darkness for millions or even billions of years. They are time capsules, perfectly preserved relics carrying the pristine chemical fingerprint of their birth. They drift through the interstellar medium, accumulating a thin frost of deep space material, until by sheer chance, their lonely trajectory intersects with our own small sunlit island in the void. These objects are the universe's own method of interstellar travel, a natural transit system for delivering the raw materials of planets from one star system to another. They are physical proof that we are not isolated. We are part of a vast interconnected galactic ecosystem where matter and information are constantly being exchanged across the stellar gulfs. The story of 3I, Atlas, is ultimately a story about connection. It began as a tale of an alien object, a thing defined by its otherness. But as we studied its mysterious transformation, it became a story about shared chemistry, about the universal processes that build worlds, and about the beautifully diverse outcomes those processes can create. It reminded us that the laws of physics and chemistry are the same everywhere, but the local conditions, the specific histories of each star system, allow for an infinite variety of expression. What we have learned from this single transient point of light is that we must be prepared for surprise. We must approach the cosmos not with a rigid set of expectations, but with an open and boundless curiosity. For every answer, we find the universe poses a dozen new and more wonderful questions. The legacy of 3I, Atlas, is this renewed sense of wonder, this urgent drive to listen more closely to the whispers from other worlds. It came to us as a blue stranger and left as a red enigma, and in that transformation, it painted a new, more vibrant, and infinitely more interesting picture of our place in the universe. We now know that the sky above us is not empty. It is a river flowing with the silent, unseen traffic of messengers from countless other shores. And we are at long last, finally building the vessels to sail out and meet them. The great interstellar hunt has begun,